In this video, we're going to continue 11.8, which was cylindrical and spherical coordinates for calculus 3. In this problem, we're going to convert this coordinate to spherical coordinates. And since the middle value is pi over 2, that seems like an unusual value for a Cartesian system. This is going to be a cylindrical setup. So we're going from cylindrical to spherical. So we have r, theta, and z, and we want to write it as rho, theta, and phi. So our theta should stay the same, right? Let's look at getting rho and z, or phi. We've got rho squared equals r squared plus z squared. That was one of our equations that we did in our last video. And we've plugged that in here. 4 squared plus -1 squared is 17. So rho equals the square root of 17. And then we had an equation for phi in terms of z and rho. Phi is cosine inverse of z over rho. We have the cosine inverse of -1 over square root of 17, which is about 1.8 radians when you plug it in. So when we write in spherical, we have root 17, pi over 2. And I could leave that as 1.8, but since I have value that looks, this looks cylindrical without having radians listed there, this looks like a z height of 1.8. So just to be a little bit clearer, I'm going to write radians there. That way, if you don't see the word spherical, you can still see these two are likely to be angles, and you'll know this is spherical coordinates. It's a good habit to get in that. Out of, again, anything with radians though, radians are unitless and you don't need to show them. That's from trig. Let's look at another example. Let's convert an equation, not a point, an equation into spherical coordinates. Z squared equals x squared plus y squared. If you remember, this was our cylindrical cones or circular cones, sorry. Let's look what happens when we plug it in though. If I plug in z, z is rho cosine phi. So z squared is rho squared cosine squared phi. And then y is rho sine phi cosine theta. I'm sorry, x is rho sine phi cosine theta. We square, each of those get squared. And y is rho sine phi sine theta. We square that, and each term gets squared because it's multiplied. This is what we get. Assuming that we have a real sphere and not just a point, rho doesn't equal 0. So I'm going to divide by rho squared. Dividing by rho squared gets me cosine squared phi on the left, and sine squared phi cosine squared theta plus sine squared phi sine squared theta. This line I factored out the theta, or factored out the phi term, sine squared phi. That leaves behind cosine squared theta plus sine squared theta. As we know from trig, that equals 1. So I have cosine squared phi equals sine squared phi. That happens along the 45-degree angles. It's maybe a little bit easier to see when we write this as tangent squared phi. 1 over tangent squared phi equals 1. So tangent phi equals plus or minus 1. This is going to get us our plus or minus pi over 4 lines. But phi is going from 0 to pi. So it's only going to give us pi over 4 and 3 pi over 4. The 5 pi over 4 and 7 pi over 4 get canceled out because they are beyond the scope of phi in this circumstance. So that's our equation though. Tangent phi equals plus or minus 1, which means we have no restrictions on rho or theta, which means that the radius can keep getting larger and larger and larger, and the actual like extending from the surface area or for the center gets larger and larger and larger. And then theta is the circle part. The circle keeps getting larger. This is where we see the circular cones getting larger. As we get further from the origin, the circular cones get larger and larger and larger. And we're going to do it along the pi over 4 and 3 pi over 4 axes for phi. So that's one way of looking at that one. Let's take a look at another problem in this section. It's a little bit more clever. Let's a little bit more challenging. We have rho equals 6 cosine phi, and we want to write this in rectangular coordinates. What I'm going to do is we don't have anything for cosine phi by itself. Not in our equations, but we do, well, without it looking ugly. It's that cosine phi is z over rho, but I don't want to put that in that as it is right now. What I'm going to do is I'm going to multiply both sides by rho. Again, I'm assuming rho doesn't equal 0, because then we just have a point. It's trivial. So I have that, but now I can rewrite that. The rho cosine phi is z. So I've got rho squared equals 6z. And we know rho squared is x squared plus y squared plus z squared. So I have x squared plus y squared plus z squared equals 6z. I gather the terms on the same side. And I've got z squared minus 6z. I do some completing of the square. Negative 6 divided by 2 is negative 3. That's there. Negative 3 squared is 9. We add 9 to both sides. And this is the equation we get. So this is a sphere of radius 3 centered at 0, 0, 3, which is a hell of a lot easier to see in rectangular system than in spherical system, simply because we're not at the origin anymore. So sometimes shifting to the other systems is helpful. It might help you picture what's going on. I can graph this a lot easier. This, I don't even know how to bend my mind around this. What do I do with theta? I don't like this. I'm not going to use this. This gives me something right away. We can also look at converting from rectangular to cylindrical or spherical. Let's choose something like one of our hyperboloids of one sheet. Let's see what both outcomes look like. X squared plus y squared minus z squared equals 1. If I go with cylindrical, I replace the x squared plus y squared with r squared, and I get r squared minus z squared equals 1. R squared equals 1 plus z squared. So the radius has a minimum of 1. And as z gets larger and larger and larger, the radius gets larger and larger and larger. Or we can look at the spherical method. This is a little tricky. What do I do with the negative z squared? So you can do some math magic. I know I have something for x squared plus y squared plus z squared. So what I'm going to do is I'm going to add in z squared and subtract a z squared. Because now that section gives me rho squared. And now I've got 2 z squareds. They're both negative. I combine them. I get rho squared minus 2z squared is equal to 1. I know z equals rho cosine phi. So I plug that in. I've got that. I'm going to factor out rho squared. I get rho squared times the quantity 1 minus 2 cosine squared phi equals 1. I divide by it, and to get rho squared by itself. I could write rho equals, in fact, let's do it. Let's get rid of the square by taking the square root of this. But this is meaningless to me. I can picture kind of what's going on here where I can't here. So I think here cylindrical is a little bit easier to read. And that'll wrap up 11.8. Next video is we're going to start, the rest of the chapter is on vectors. So if you've taken physics and explored vectors, you're in a good spot. Peace.